Late November 1944. The muddy borderlands between France and Germany. It is raining, and the mud is deep enough to swallow a man's boots. Instantly, the tank violently slews to the right and grinds to a dead halt, nose-diving into the mud. This specific diagnosis dictates the tank's fate. The U.S. Army divided repair work into strictly defined echelons. First echelon work belonged to the crew itself, focusing on tightening tracks and daily engine maintenance. Second echelon fell to the battalion's own mechanics, equipped with light trucks and hand tools, capable of swapping a carburetor or replacing a ruined road wheel. But this Sherman requires heavy surgery. The shattered final drive involves thousands of pounds of cast steel and complex internal gearing. Patching the pierced armor requires specialized, high-amperage welding rigs to restore the ballistic integrity of the hull. The frontline battalion mechanics do not have the heavy cranes, the industrial arc welders, or the time. If they attempt to rebuild this machine in the mud, they will fall behind the advancing infantry. Therefore, the officer makes a rapid, calculated decision. He marks the tank for evacuation to the third echelon. It is officially classified as heavily damaged, but fully recoverable. Another, much larger transport will soon arrive in the night. It is an M25 tank transporter, an immense armored truck and trailer combination, known to the crews as the Dragon Wagon. It will winch the bleeding Sherman onto its long flatbed. A thick, ominous plume of grey smoke jets from the driver's hatch. Seconds later, the top hatches fly open and haul it further away from the sound of the guns. By filtering the wreckage just miles from the fighting, the Army ensured that only salvageable machines moved backward and only to facilities properly equipped to handle them. But this creates a new, profound logistical challenge. The tank is now miles behind the front line, requiring the kind of heavy industrial manufacturing usually found in Michigan or Ohio. Where exactly does a mechanized army find a heavy machinery factory hidden in the muddy forests of wartime Europe? 10 miles behind the front line, the deep roar of the M25 Dragon Wagon's engine drops an octave as the driver downshifts. The massive truck and its flatbed trailer carry the crippled Sherman into a dense, heavily camouflaged pine forest. Here, the artillery fire is reduced to a dull, distant thud, replaced by a much sharper, localized noise. It is the blinding crackle of high-amperage arc welders, the rhythmic pounding of sledgehammers, and the constant hum of portable gasoline generators. This is an ordnance-heavy maintenance company. It looks like a scrapyard, but it operates with the cold precision of a Detroit assembly line. The military realized that shipping heavily damaged tanks all the way back to port cities in England or the United States would take months. 4 American crewmen scramble frantically from the smoking steel, drop into the mud, and disappear into the safety of the brush. Time the frontline units did not have. Instead, they brought the factory to the mud, underneath sprawling camouflage nets. Hundreds of mechanics, machinists, and welders work in rotating shifts, 24 hours a day, regardless of freezing rain or blackout conditions. The M25 lowers its ramps, and heavy winches drag the wounded Sherman off the trailer. Immediately, a crew of specialists descends upon the hull. They do not work gently. To fix the catastrophic damage caused by the German armor-piercing shell, they must first perform an amputation. At the front of the vehicle, a welder ignites an oxyacetylene torch. He cuts away the jagged, warped steel around the 75mm entry wound, creating a clean, rectangular window into the crew compartment. He is not trying to melt the hole shut. Armor plate cannot be repaired by simply filling it with brittle slag. Instead, a crane drops a pre-cut slab of thick, salvaged steel over the gap. The welder runs a continuous, blinding bead of molten metal around the edges, fusing the patch to the glacis plate. It leaves a heavy raised scar on the tank's nose, but the ballistic integrity of the hull is completely restored. Simultaneously, a massive 10-ton wrecker truck backs up to the shattered right side of the tank. For the German gun crew, this is a mathematical certainty. They have achieved a hard kill. The German shell destroyed the heavy final drive housing, the immense cast steel bulb that houses the gears turning the drive sprocket. In any previous war, replacing a transmission component this large would require a permanent dry dock and a gantry crane. Here in the forest, mechanics unbolt the ruined housing and hook chains around the casing. The wrecker's boom whines, lifting the jagged, oil-soaked mass of steel entirely away from the tank and dropping it unceremoniously into the mud. The speed of this operation is deliberate. The heavy maintenance companies operate under a ruthless philosophy. They do not manufacture, they swap out. By removing entire modular assemblies rather than trying to fix individual broken gears inside a shattered casing, they drastically compress the timeline of repair. What would take a week in a pristine civilian factory is executed overnight in the freezing damp of a European forest. By dawn, the Sherman has a sealed hull and a massive empty cavity where its right final drive used to be. The mechanics are ready to install the replacement, but this brutal efficiency relies on a profound logistical assumption. Lifting broken steel out of a tank is only half the equation. According to the laws of attrition that govern this theater of war, that Sherman is now a permanent casualty. Putting the machine back together requires thousands of pounds of fresh, perfectly machined components. A heavy maintenance unit cannot pour liquid steel and forge complex gears in the dirt. To finalize the resurrection of this 30-ton weapon, they must reach for a replacement part, confident that it will exist, and more importantly, that it will slide seamlessly into place. A heavy cargo truck backs into the clearing, its tires spinning briefly in the churned earth. The tailgate drops, revealing massive wooden crates stenciled with shipping codes from the United States. A crane lowers its hook, lifting a 3,000-pound final drive assembly from its pine box. The steel is pristine, coated in a thick layer of cosmoline to protect it from the salty ocean air during its Atlantic crossing. The mechanics wipe away the greasy preservative. The crane swings the heavy, bulbous casing toward the empty cavity on the right side of the Sherman. This is the moment where the entire American armored system either works or fails. The Sherman hull, waiting in the mud, was assembled by the Fisher Body Plant in Michigan. The replacement final drive swinging from the crane was cast months later. It is 30 tons of dead iron blocking an artery of the Allied advance. The gunner will report the destruction by the Chrysler Detroit Arsenal. They were built by different workers in different factories, hundreds of miles apart. Yet, as the crane operator carefully lowers the massive gear housing into the gaping hole of the hull, the mechanics do not reach for metal files, grinders, or shims. They reach for heavy wrenches. With a dull metallic thud, the housing seats perfectly against the armor. Dozens of heavy bolt holes align to the fraction of an inch. The mechanics drive the bolts home, torquing them down through the freezing rain. The part fits exactly. To modernize, this seems entirely normal. But in the context of a 1,944 European battlefield, this level of absolute interchangeability was a profound weapon of war. Other nations, despite their fearsome reputations for engineering, operated under different industrial philosophies. The German war machine often built tanks as bespoke pieces of heavy craftsmanship. Factories made constant, localized adjustments to armor plates, drivetrains, and suspensions. If a German mechanic in the field needed to replace a shattered transmission on a heavy tank, He often found that the new part did not fit the old hull without extensive hand-fitting, grinding, and specialized labor. The manufacturing tolerances drifted from batch to batch. The American military treated the Sherman not as a custom chariot, but as an automotive appliance. Before the first tank ever rolled off an assembly line, an officer will mark a tally in a ledger, and the German High Command will subtract one more tank from the industrial output of the United States. The Ordnance Department enforced a rigid doctrine of standardized blueprints. Tolerances were strict. A bolt threaded in Detroit was perfectly identical to a bolt threaded in Ohio. This meant that the logistical supply chain did not need to track which specific factory built which specific tank on the front line. They only needed to push an iron river of standardized spare parts across the Atlantic and directly into the hidden forest workshops. Within hours, the mechanics thread a fresh length of steel track around the newly installed drive sprocket. They refill the engine oil and bleed the hydraulic lines. The driver climbs into the compartment, primes the engine, and hits the starter. The massive radial power plant coughs, spits a cloud of blue smoke, and settles into a steady, vibrating roar. The tank lurches forward, its new tracks biting into the forest floor. The machine has been resurrected. It is whole, lethal, and ready for combat. But an assembly line hidden in the woods is only half of the equation. The true test of this system is not how fast the mechanics can tighten a bolt. The test is what happens when this patched, welded, recycled machine is pushed back into the brutal realities of the forward line, right back into the sights of the enemy who thought they had already killed it. To the men holding the defensive line, a disabled tank abandoned by its crew is a tombstone. It will rust exactly where it died. When the patched Sherman rolls out of the tree line and back onto the contested muddy road, the heavy, raised scar of fresh weld on its nose represents far more than a repaired vehicle. It represents the complete collapse of the German defensive strategy. For months, the Wehrmacht commanders defending the western frontier had operated under a strict arithmetic illusion. They understood they were heavily outnumbered by American industry. Their strategy relied on bleeding the Allied columns at choke points, trading ground for time, and tallying the destroyed hulls. A German anti-tank battalion might claim 20 Sherman kills in a single grueling week of combat. According to the traditional ledgers of war, the opposing American armored thrust should be entirely spent, its momentum shattered, and its surviving infantry forced to halt and wait weeks for new tanks to ship from overseas. Yet, just days later, the morning fog would lift to reveal the exact same American unit, advancing with full armored strength. To the exhausted German defenders looking through their optics, the math simply did not make sense. The discrepancy lay in how the two armies defined a casualty. To the German command, a shattered track. This belief makes perfect sense. Throughout the history of mechanized warfare, a broken machine on a contested road was a lost machine. A pierced hull and an abandoned vehicle equated to a permanent kill. But to the American ordnance battalions, a tank was never truly dead until its hull was burned to ash or blown into unrecoverable fragments by an internal ammunition detonation. Everything else was merely a temporary mechanical delay. This hidden recycling loop broke the fundamental rules of attrition. The American advantage in Europe was not solely dictated by the raw number of fresh Shermans rolling off transport ships at Cherbourg or Antwerp. The true battlefield dominance was driven by the operational readiness rate. The system ensured that the armored units, at the very tip of the spear, rarely lost their mass. A replacement crew, arriving fresh from a staging depot, would simply be assigned to the newly welded tank. They would climb into a machine that still smelled faintly of burned diesel and hot iron, power up the engine, and immediately rejoin the platoon's formation. While the German gunners were spending their irreplaceable tungsten ammunition, risking their lives, and burning their dwindling fuel reserves to halt an advance, they were often achieving nothing more than a 72-hour delay. The American tanks they proudly marked as destroyed. The Wehrmacht relies heavily on this brutal arithmetic. They believe they do not need to push the Americans back to the beaches, were secretly dragged away, operated upon in the forest, and fed right back into the line of contact. This created a crushing psychological burden for the frontline defenders. A German crew might fight flawlessly, score a perfect kinetic strike, survive the return fire, and hold their ground, only to face the very metal they thought they had already beaten. The physical evidence of their hard-fought victories was continually erased. The system of recovery and standardized repair was an undeniable tactical triumph. The opposing forces were not blind. German forward observers frequently watched American M32 armored recovery vehicles hauling smoking wrecks out of the mud. They understood exactly what was happening behind the lines. But understanding the mechanism and possessing the ability to replicate it are two entirely different things. If the battlefield recycling of armor was so visible and so devastatingly effective, why was the German military entirely incapable of doing the exact same thing to save its own dying tanks? Just a few miles across the lines, a German Panther tank sits paralyzed in the identical freezing mud. It has not been struck by enemy fire. Its heavy transmission has simply shattered under the immense strain of the vehicle's own 45-ton weight. A German gunner sits behind the steel shield of a PA K-40 anti-tank gun, watching a narrow gap in the shattered tree line. They only need to bleed their armored columns until the advance collapses under the weight of its own burned-out wrecks. To the German crew, this mechanical failure is just as lethal as an armor-piercing shell. They are facing the exact same tactical problem as the Americans, a disabled machine blocking a vital route, yet their response exposes the fatal flaw of their engineering doctrine. The German war machine possessed armored recovery vehicles, most notably the Panther, and they employed highly skilled mechanics. But their repair system was crushed by the sheer complexity of the weapons they were trying to save. The Panther was a masterpiece of lethality, heavily armored and equipped with a devastating long-barreled gun. However, it was radically over-engineered for the brutal realities of forward field maintenance. If a German mechanic needs to replace a shattered transmission in the forest, he cannot simply unbolt a modular housing from the front of the tank, like his American counterpart. On a Panther, the transmission is buried deep inside the hull beneath the turret. To access it, the repair crews must rip out the interior compartments, unbolt heavy armored roof sections, and frequently require specialized heavy gantry cranes to lift the massive turret completely away from the chassis. These tools rarely exist within range of enemy artillery. The running gear poses an even darker trap, but 3 days later, the rain clears, and the American armored column pushes forward again. The German gunner looks through his optical sight. To distribute the immense weight of their heavy armor, German designers utilized a complex system of overlapping, interleaved road wheels. On a dry test track, this provided a remarkably stable firing platform. In the freezing rain of late 1944, it is a logistical death sentence. The thick mud packs tightly between the overlapping steel discs and freezes solid overnight, physically locking the tracks in place. If a single inner wheel strikes a mine and shatters, the recovery crew cannot simply swap out the broken part. They must carefully unbolt and remove up to 5 heavy outer wheels just to reach the damaged inner one, balancing the heavy metal in the mud while exposed to mortar fire. Because rapid forward repair is mathematically and physically impossible, the German crew has only 2 options: They can wait for scarce heavy rail transport to haul the machine hundreds of miles back to a factory in Germany, a luxury their collapsing rail network can no longer afford. Or they can drop a thermite grenade down the open hatch, destroying their own weapon to prevent capture. This was the engineering trap. The Wehrmacht prioritized the individual, tactical superiority of the tank over the logistical survival of the armored fleet. A weapon that cannot be repaired under combat conditions is ultimately a disposable weapon. The invisible American system thrived precisely because it avoided this trap. Scanning the approaching line of olive drab, he zeroes in on the lead Sherman. And then he sees something. It ensured that an armored column retained its mass, bending the laws of attrition until the enemy simply ran out of guns. But this mechanical illusion of an endless, immortal army was not a bloodless equation. The steel did not heal itself. Behind the neat ledgers of operational readiness and standardized parts, there was a profound, exhausting human toll required to keep the Iron River flowing. To understand the true nature of this resurrected armor, we must look closely at what happened when a replacement crew finally climbed into a freshly welded machine. Deep in the rear staging area, a replacement crew walks through the freezing rain toward their assigned vehicle. They are replacements, recently shipped across the Atlantic, expecting a pristine machine straight from a Detroit assembly line. Instead, the supply officer hands them the paperwork for a veteran Sherman. As the young tank commander steps onto the track and pulls himself onto the hull, his boots slip on wet steel. He immediately notices the thick, raised scar of a fresh weld on the front glacis plate. The exterior has been hastily repainted with fresh olive drab, but the interior tells a much darker, undeniable story. Preparing a recovered tank for a new crew was a grim, visceral necessity. Before the newly installed engine could be primed, that defies the absolute laws of battlefield mathematics. It is the exact same tank. He recognizes the tactical markings painted on the turret, or the radio operators could plug in their headsets. The fighting compartment had to be meticulously sanitized. The heavy maintenance companies did not just replace shattered drive sprockets. They had to prepare a tomb for the living. Low-ranking clerks, mechanics, and unnamed laborers, armed with wire brushes, buckets of freezing water, and strong chemical solvents, had to scrub the interior steel. They worked in tight, suffocating spaces to wash away the scorched paint, the spilled hydraulic fluid, the dried blood, and the lingering, acrid scent of vaporized metal. The new tankers had to strap into the exact seats, where the previous occupants had absorbed a 75mm kinetic strike. The illusion of an immortal, endless armored force was strictly a weapon deployed against the enemy. The men operating the machinery knew exactly how fragile the steel really was. This was the heavy human toll of the American logistical triumph. The defining question on that contested European road was never merely about who possessed the thickest armor plate or the highest velocity gun. It was about which military doctrine could absorb the absolute certainty of attrition and continue moving forward. The German High Command engineered exquisite, individual machines. He recognizes the specific warped dent on the front right fender, but where his armor-piercing shell had punched a hole that required a perfect environment to survive. The United States built an entire, sprawling architecture of recovery around an imperfect machine fully expected to bleed. That invisible system was not a miracle. It was an unbroken chain of human labor. It was sustained by the recovery crews dragging 60,000-pound steel cables through the mud under artillery fire, the battalion officers running triage in the dark, the engineers and factory workers who standardized the threading on 1,000 individual bolts, and the welders working 24-hour shifts beneath camouflage nets. They fought a parallel war of sheer endurance, wielding heavy wrenches and oxyacetylene torches to reverse the destruction of the front line. When the German anti-tank gunner peers through his optics and watches the dead Sherman return, he is not witnessing a mathematical impossibility. He is looking at the final, terrifying output of an industrial nation mobilized down to the inch. The patched tank grinding up the muddy rise is not a phantom. It is 30 tons of recycled iron, propelled by human exhaustion, tracking its gun directly back toward the tree line. Through the steel, just 72 hours earlier, there is now a thick, heavy scar of fresh weld. The destroyed track is whole. The shattered drive sprocket is completely intact. The dead tank is not only moving, its main gun is tracking directly toward his position. To the German defender, this feels like an impossibility. It is as if the enemy is fighting with an immortal army, where destroyed machines simply refuse to stay dead. But there was no magic involved in this resurrection. What the gunner was witnessing was the output of an invisible system. The air smells of wet pine, diesel exhaust, and old cordite. He knows the heavy rhythmic thrum of the approaching engine, operating just beyond his line of sight. To understand how this 30-ton wreck returned to the fight, we first need to look at the violent seconds immediately following the impact, and why the survival of the men inside was the first vital step in a much larger machine. When the German 75mm shell struck the Sherman, the reality inside the fighting compartment was violently rewritten in a fraction of a second. The crew inside did not hear a distant, muffled crack. They felt a concussive, deafening shockwave that instantly sucked the oxygen from their lungs. As the solid, armor-piercing penetrator punched through the front glacis plate, it brought the outside world in. The sheer kinetic energy overmatched the armor, spraying the interior with white-hot metal fragments known as spalling. This high-velocity shrapnel ricocheted relentlessly off the cold steel walls, severing hydraulic lines, shattering optics, and filling the air with the smell of vaporized steel and hot grease. To the German gunner watching from the tree line, the expected outcome was a catastrophic explosion. Early in the war, American armor had suffered a grim, fatal flaw. Their ammunition racks were stored in dry bins along the upper sides of the hull. A direct hit or a piece of hot spall almost guaranteed an immediate, violent ammunition fire, turning the vehicle into a furnace before the men could react. Long before the olive-drab silhouette finally breaks through the autumn fog, it is an American Sherman tank grinding slowly up the rutted road. But this late-model Sherman was different. It carried a hidden engineering adjustment directly beneath the floorboards. The main gun shells had been relocated deep inside the hull and encased in wet stowage bins, metal jackets filled with a chemical mixture of water, ethylene glycol, and rust inhibitors. When the German shell and subsequent shrapnel pierced these lower compartments, the liquid bled out, chemically smothering the initial sparks and delaying the ignition of the cordite propellant. It did not make the Sherman fireproof. The tank was still bleeding diesel fuel and filling with acrid, choking smoke. But the wet stowage bought the crew something infinitely more valuable than a pristine vehicle. It bought them time. In a disabled, smoking tank, a crew had a lethal window of about 10 seconds to evacuate before they were asphyxiated. Recognizing this harsh battlefield reality, American ordnance designers had studied earlier casualty reports and fundamentally altered the tank's architecture to prioritize escape. The hatches above the driver and assistant driver were widened. More crucially, they were spring-loaded. A stunned, injured man choking on smoke did not have to heave 80 pounds of dead steel upward against gravity. He only had to release an interior latch, and heavy torsion springs violently snapped the hatch open. As the surviving crew scrambled over the turret and dropped into the cold mud, The true resilience of the American system was already at work. The gunner is a veteran. He does not panic, and he does not fire early. He tracks the vehicle through his optics. The men crawling through the ditch were not a tragic byproduct of a lost machine. They were the single most difficult component of the weapon system to replace. A heavy machinery plant in Michigan could weld and assemble a new Sherman hull in a matter of hours. But it took months of specialized training, mechanical coordination, and the brutal, unteachable lessons of live combat to forge a veteran tank crew. By engineering the vehicle to prioritize human survival, the military ensured that tactical experience was not burned away in a single ambush. The men lived to fight again, but as the tankers retreated toward the American lines, their shattered Sherman remained firmly lodged in the mud, a smoking roadblock halting the entire armored column. It weighed 30 tons. Its right track was completely severed, its heavy drive sprocket was destroyed, and its transmission was jammed in place. The survival of the men was only the first phase of the equation. The next immediate problem was a matter of heavy physics. How does an advancing army physically drag 30 tons of dead, immovable steel out of a kill zone while the enemy's guns are still dialed in on the road? The stalled column sits in the freezing rain. Behind the knocked-out Sherman, the road is completely blocked. The German gunner in the tree line knows this. He waits, expecting the Americans to send unprotected infantry forward to clear the route, mentally calculating the distance at exactly 400 meters. He waits for the Sherman to expose its slightly thinner, lower hull, or soft-skinned trucks that his Pak-40 can easily shred. Instead, the heavy thrum of a radial engine announces the arrival of a distinctly ugly, specialized machine. It is an M32 armored recovery vehicle. Built on the identical chassis of a standard Sherman, it possesses the same thick armor and tracks, but its main fighting turret has been removed. In its place sits a massive, welded A-frame boom crane, an A-frame mortar for laying smoke, and a 60,000-pound mechanical winch. This is the first moving piece of the American armored resurrection cycle. The recovery crew does not wait for the artillery to stop. 4 ordnance mechanics, their coveralls soaked in diesel and freezing mud, drop from the M32 into the contested zone. They are not there to return fire. Their job is manual, heavy labor under direct enemy observation. They drag thick, braided steel cables through the rutted earth, ducking as mortar shrapnel snaps through the bare branches overhead. Hooking a 30-ton deadweight is a brutal physical task. The tow pintles on the disabled Sherman are buried in the muck. The men have to dig by hand, securing the heavy steel D-rings while the enemy actively tries to kill them. Once the cables are locked, the M32 reverses. The winch takes up the slack. The braided steel line snaps taut, vibrating like a massive bowstring, as it climbs a slight rise in the terrain. Then he pulls the firing lever. The 75mm armor-piercing shell. Pulling a disabled tank is entirely different from driving one. Because the Sherman's right track is severed and the drive sprocket is shattered, the right side of the tank cannot roll. It acts as a massive steel plow. As the recovery vehicle's engine roars, the dead Sherman resists. The mud builds up in a thick wave against the front hull. For a few agonizing seconds, the winch groans, and the M32's own tracks spin uselessly in the sludge. Then, the immense torque wins. With a sickening scrape of metal against rock, the knocked-out tank breaks free of its crater and begins to slide backward. This immediate, mechanized response was a core tactical doctrine. Other armies often relied on underpowered half-tracks to pull disabled armor, frequently burning out clutches and failing to move the sheer mass. Alternatively, they waited until nightfall, leaving the battlefield littered with stalled vehicles. The American Ordnance Battalions embedded heavy recovery vehicles directly behind the fighting elements. They treated broken tanks not as static monuments, but as immediate logistical obstacles that had to be cleared while the guns were still hot. The M32 drags the smoking Sherman backward for half a mile, pulling it around a bend in the road and behind the shattered stone walls of a ruined farmhouse. The immediate tactical crisis is solved. The route is clear, and the armored column can resume its advance, crosses the distance in less than half a second. The kinetic impact is a deafening, metallic crack that echoes flatly through the valley, but the recovery crew's job ends here in the wet grass. They drop the towing cables and turn back toward the sound of the guns, leaving the ruined vehicle behind. The Sherman is out of the kill zone, but it is entirely useless. It is bleeding oil, its armor is compromised, and its internal drive mechanisms are violently deformed. Dragging it out of the mud was merely a matter of brute force. The real problem requires precision. Someone now has to look at the torn metal and make a rapid, calculated decision. Is this an unsalvageable pile of scrap to be stripped for parts, or is it a machine that can be saved? Behind the ruined farmhouse, the smoking Sherman is no longer a tactical problem. It has become a logistical puzzle. A jeep pulls into the wet grass, and a battalion maintenance officer steps out into the freezing rain. He is not a combat commander. He is an automotive diagnostician, trained to look at shattered steel and read the exact violent history of its mechanical failure. He circles the tank, his boots sinking into the mud. He wipes away thick grease and burnt paint to find structural truths. The tungsten cord round shatters the Sherman's right track, tears through the heavy drive sprocket, and punches a neat, fatal hole through the lower frontal armor. The sharp, metallic tang of vaporized steel still hangs in the damp air. His job is forensic triage. The American military recognized early in the war that clogging their own supply lines with useless scrap metal was just as dangerous as losing tanks to enemy fire. If every damaged vehicle was dragged blindly to the rear, the repair depots would be paralyzed by the sheer volume of dead iron. To prevent this, the Army instituted a rigid, unsentimental system of categorization. The officer inspects the kinetic entry wound. It is a clean 75mm hole through the lower front glacis plate. It was deadly to the crew compartment, but mechanically, it is just a localized puncture. He checks the turret ring to ensure the concussive force did not warp the heavy circular bearing that allows the gun to traverse. He opens the rear engine louvers. There is no fire damage reaching the power plant. The central drive shaft running beneath the floorboards remains perfectly straight, but the right side of the vehicle is a catastrophic mess. The armor-piercing shell shattered the massive drive sprocket, snapped the heavy steel track, and destroyed the final drive assembly that transfers rotational power to the ground.